honorable speaker is Professor Ingrid Verbauwhede from KU Leuven. I know Ingrid Verbauwhede for a long time. It is actually, we don't have enough time that I just list all her awards and all her background, but I know she was studying hardware-related topics, because it's not only hardware design, FPGAs, but also hardware security. She belongs to the pillar of these communities for a long time. She studied at UCLA. I think you did a PhD there.
No, I was teaching.
Teaching, okay. And but PhD you did at Leuven.
PhD was at Leuven.
And she is recipient of 2 times ERC, which is a very competitive award in a research award in Europe. She's also recipient of IEEE awards for her contributions to system design and hardware design. And she's also doing a number of original works and contributions in the area of hardware security. So I'm really happy that she said yes, because she's also very busy, but chairing a number of conferences, and she's now here. And I hope that she enjoys this time, because every one of us, as she also told me today, wants kind of real people in front of them. So we have some real people here. And Ingrid, the stage is yours.
Thank you. Thank you for the introduction. Yes, so I really like people here. I hope people come from the coffee back into the room at some point. And Ahmad asked me to intertwine a bit into not make just a research presentation, but also my personal experience. Many topics that I heard during the panel, I think also relate to topics that I felt. What it is, certainly when I was a junior professor, people would ask me, where is the secretary of, or are you the secretary of Professor Verbauwhede? And then I had to say, no, I'm the professor. So that phase I've passed, right? Join audio to start speaking. Should I push a button? No, just ignore. Okay. So my first slide is actually, you would think, what does this has to do with this? Today, actually, there is a celebration at what's called the KVAB. That's the Royal Flemish Academy of Belgium. So that's a Royal Society in Belgium. And they have a presentation, or a visionary presentation, on Professor Roger van Overstraeten. You probably wonder who is this and why is this important to my presentation? Why is this important? For those, maybe I don't know how many of you know, but Van Overstraeten was actually the founder of IMEC. And IMEC at this moment, if you're in semiconductor industry, is a research institute which even gets into The Economist a couple of weeks ago. And they employ like 4,000 or 5,000 people. And The Economist calls this is a research center pure on semiconductor technology. And they say this is the brain trust at the heart of the $550 billion semiconductor industry. Why is this important? Because he's the guy, he convinced my father that I could start engineering. And so he made time, when I was 16 years old, he made time to talk to me and my father and get his permission, get permission of my father to start engineering. Otherwise, maybe I wouldn't have been here, right? And so even big shots, call it a mentor or a luck in your life, big shots have make sometimes time to talk to a father and his daughter to start and allow me to start engineering. And since then, now I'm also a member of this Royal Society, which is extremely male dominated because it's an old man's club usually. And so today I even don't attend. So what is this presentation about? So what I want to convince to you is why hardware security has become so important. Hardware security did not exist when I was a PhD student. And so how did I end up in this field? And of course, after me, Nele, Leila, and many other women ended up in this field. So I belong to a research group, which is called COSIC, Computer Security Industrial Cryptography. A couple of facts here. I'm a professor in Leuven since 2003. Before that, I was a professor at UCLA in Los Angeles, although I was not hired to work on hardware security. There was a different description. You will see that later. And before that, I spent quite some years in Silicon Valley and at UC Berkeley, not working on hardware security because there was no funding for that. So my interest is in low power embedded systems, IoT, cloud. For ASICs and FPGAs. FPGAs, we had the previous presentations are very important in my research, and I apply them to security and cryptography. But I did start in hardware security. My PhD work was actually in that topic. And for my PhD, I made a programmable DES processor. And you probably wonder what is DES? DES stands for the Data Encryption Standard. It was actually the first encryption standard. And we made some chips. So actually it was what now is called a domain-specific processor. This thing could be programmed several modes of operation. You can set it up as a pseudorandom number generator, things like that. Now, after my chat with Professor Van Overstraten, because I was good in math and physics, but I didn't want to become a math and physics teacher. That would be the career that my parents and lots of people in my environment were pushing me into. I said, no way, I'm going to be a math and physics teacher. I didn't like that. And so I want to do maybe circuits for medical applications. Couldn't find a PhD position on that. And so actually I ended up making circuits or a chip for hardware security. And that was the start. So after my PhD, there are actually no jobs in hardware security. Those that did hardware security were probably all working for NSA, never published, was not known. So, but I did move to the US as a postdoctoral researcher, and I had to change subjects. So I worked on DSP processors and synthesis tools for DSPs and things like that. And I did at UC Berkeley, worked on small companies in Silicon Valley. I can also tell you what are not so interesting experiences working for small companies, what can go wrong. Until actually UCLA called, and they wanted someone with my experience doing integrated circuit, digital design, but they wanted that for wireless communication. This was the time that companies like Broadcom, Qualcomm, and all these were popping up. They were spin-offs of companies, spin-offs of the universities, because Broadcom, for instance, started at UCLA. I said, yes, I can do that. I didn't have much of confidence because what did I know about wireless communication? But I used that, and actually that's where I started my research in hardware security while I started at UCLA. One of the problems was, and that's also mentioned, maybe it's the same problem when you start a company, is getting funding. Since there is no one working in hardware security, the National Science Foundation, which is a bit equivalent to the DFG or other societies, they didn't have a call on hardware security. Now they have lots of calls on hardware security, but they had a program which was called Design Automation for Micro and Nano Systems. So it was actually a program where they called inputs or requests for proposals in electronic design automation. And so what I decided then is that let's go and call my proposal VLSI design methods, but it was actually for low power embedded encryption. So that's how I ended up, and that's how actually the research started. Then I moved back to Leuven, and Leuven is a powerhouse in security and cryptography. We even hit the Wall Street Journal at some point, and COSIC is called a security powerhouse. In Belgium, an encryption powerhouse rises. University of Leuven has become a battleground in the fight between privacy and surveillance. So and this is a picture of my lab, actually the old lab. Since then we have a new lab with some people on scopes and doing side channel attacks and things like that. So, but COSIC is much bigger than me. So we're close to 100 people now. Details are maybe not so important. We have quite a lot of postdocs, but we also have some diversity in the sense that we are 7 professors, Bart Perneel, myself, Vincent, and so on, but we have 3 out of 7 are female. Nele is maybe only half time anymore, but we still count her as part of COSIC. So let's start a little bit more technical now. So why do we still interested in still interested in hardware security, and in my opinion, it's a field that's not going to go away. We still have next generation, what I call next generation embedded systems. We had quite some introductions today on that. For instance, cyber physical systems or cars. We're here in Germany. So these are networked embedded systems interacting with the environment. So to have a cyber physical system, so you need to have it distributed, you have to have it networked, but it also interacts with the environment. It's full of sensors. You can imagine that these things, of course, need a lot of security. One example here, which is a bit old, is like an attack on the network system in the car, where you see that the car is in park. The car is in park, but the odometer, this is still an analog odometer or a fake analog odometer, goes all the way to 140. You can see from this is an American car because it's miles per hour, but it's parked and it has some other funny messages. Also in Leuven and in Europe, there's lots of attacks on cars and car infrastructure. So in Leuven now we have quite some, all the key locks of the Teslas have been broken. And this thing is not going to stop, because this is a picture that I took from the newspaper in Belgium, in Flanders. And this is one company, semiconductor company, which we have in Flanders. It's called Melexis. Melexis makes sensors, sensors for car applications. And one car will have at least 32 different sensors only from Melexis. So in total, maybe the total amount of distributed components on the car is much more than the 32 chips of Melexis, but also, for instance, the hundreds of microcontrollers. Everything is being can be attacked, needs protection, and so on. But for the hardware designer, it's difficult because, of course, they don't want to pay. They don't want to pay in area. They don't want to pay in throughput or reduced throughput. They actually also, especially what we're concerned about, is the power and energy constraints. So power is limited. And that's the case, for instance, if you want to add security to RFID tags. Power is also an issue for cooling. Cooling is a big problem. Of course, we know the cooling problems in big cloud infrastructure or cloud infrastructure like this picture, or this is the cooling infrastructure of a picture that I took from the newspaper. And looking at these colors, this is kind of a Google colors. But cooling is also important for embedded devices, implantable devices. If you have a pacemaker implant, you know that the temperature can only rise by maximum 1 degree Celsius, because above that, it becomes uncomfortable for the patient. You don't see this, but I have an announcement here that I should buy a license from something. Can you remove this, please? Team viewer, go. Okay, so we have to worry when we add security, this implantable device, that we stay within the power and the energy budget. So this is for cooling reasons, we worry about power. For, of course, the energy, we worry for the battery life itself. Because a pacemaker has a battery which is non-rechargeable, which means if you add security and the lifetime of your device goes down, say, for instance, instead of having to replace the pacemaker every 10 years, you now have to replace it every 5 years, no patient will accept that, right? So we cannot, we're asked to add security, but it shouldn't cost anything. So we have to worry how much crypto can we get out of 1 microjoule. And we did some studies on that. You can also ask, is there really a problem with security in IoT? Many of these devices are just cheap devices. Why should I care about security? And many of devices now get connected to the internet without too much of a problem, right? So before we had the Internet of Things, we had cheap devices. People would put a camera, a CCD camera on their garage door, and they would watch from the inside who's ringing at the door. So you had a camera and you had some monitor somewhere inside at your front door who's ringing the door. Now this can be used for video protection or video surveillance. It depends how you watch at it. The problem actually becomes that this cheap camera now gets a wireless connection. It's connected to the cloud, and we had some cloud examples before. And from the cloud now it goes to your phone, some app in the phone. And it's actually this combination, the fact that you have a cheap device and you connect it to the phone, that makes it unsecure. Aurélien Franquillon calls this composition kills. It's the fact that you have two components that you connect together that makes it actually dangerous, because the camera by itself or the app by itself might not be an issue. And so as a consequence, with this experiment, he could find multiple cameras everywhere in France, and he could watch the internals of many people's rooms and driveways and even bedrooms and so on. So this needs to stop. So what's the consequence of adding or the internet to this simple camera? The consequence is now that the attack surfaces increase, right? So instead of just locally, you have a distributed attack surface. Devices which were not designed for security, they now go online. And the threat model thus has changed. And so the value is increased just by being online. So when people put it there and they forget about it. So this little camera, if it has a microcontroller there, when do you change it, right? When do you update the software for it? So the challenge for us hardware designers is that we have to adapt to this situation, right? So connected devices, they're not immune anymore to compromise. Security devices like smart card are pretty secure. We have a hard time to break them, hard time to put side channel attacks on them. But it's the fact that we rely on all these non-cheap security devices for daily security and privacy. That's why we have problems. Unfortunately, many of these embedded devices, they're obscure, they're hidden. So we are requested to update the operating system on our laptop. And so we get these warnings in the office also, please update, do this, do that. But these cheap devices like the fridge, or today I saw someone who can remotely start his coffee machine. When was the last time that this was updated, right? And even for a hardware designer, this is an issue. Say you develop an IP module, say for an AES encryption engine. So it could be still secure in one situation, but it might change. It might change if that IP module is included somewhere else, right? So you might have changing security protection layer depending on where you're going to use this IP. So that's together with the say power, performance, area, throughput specifications, there should be security specifications. And it's simple, and it only gets worse. This is a story by itself. You see many different examples. You could say all little IoT devices that can be hacked, and some comic made actually big story out of it. I'm going to leave this for you to read later when you look at the slides. They all go berserk, right? And it's not just fantasy. We had in our lab a mobile or self-driving vacuum cleaner, and actually the PhD student could control vacuum cleaners all the way up to China, where this vacuum cleaner was coming from. So this is how far it goes, right? Now, how do we address this problem? We should actually think, and that's why I come to the story of the root of trust. We have to carefully think, what do we trust, and where are our trust boundaries? And we actually want to minimize what needs to be trust. And these definitions come a bit from the trusted computing setup, but also in general, right? Trust is defined by Ross Anderson in his book, Security Engineering. It's a trusted system of component is one whose failure can break the security policy. But a trustworthy system or component is one that won't fail. So there's a clear difference between something which is trusted and something which is trustworthy. And we want to minimize what needs to be trusted, because then it goes wrong, right? The trusted computing group has a little bit of a similar definition. An entity can be trusted if it always behaves in the expected manner for the intended purpose. So what it's supposed to do, it should do well. Loosely stated, for us hardware designers, if a trusted system or component fails, just bad things can happen. And that's why we actually want to minimize what needs to be trusted. But this is really the goal of security. Try to minimize what needs to be trusted. If that secure root of trust fails, then you might have a major issue. But the rest should have some composition rules based on minimum root of trust. And that root of trust can even change depending on the situation, right? So you can trust, for instance, both your brother and your banker, but the trust is also action specific. So it's okay to do one job, but not another. So you can trust your brother to watch your son, but you should not trust him maybe with your bunny. And the other way around for your banker. You want to trust the banker to watch the money, but maybe not the son. So this is action specific, and it also can evolve over time, right? We re-evaluate trust decision maybe on a frequent basis. Maybe we need re-evaluation for every action that we take, and that kind of is also about trust. So pictures are gone. This is probably with the transfer, but basically on this slide I had two pictures. To the left was just a desktop, and to the right was a server room. This is the old situation, and still this the case in many companies. And then what do we trust and what we don't trust? You would trust the PC or the laptop in the room, and you would also trust, this thing jumps, you would also trust maybe the server room. But we would develop crypto, and we developed security protocols to protect this communication channel. This is where we say, okay, this is where the problem can occur. The attacker sits on that communication channel, but the attacker sits on that communication channel, but the actual modules or the laptops or the servers are the ones that operate in black boxes. There is no problems there. So we have protection by strong mathematical algorithms and protocols. And before the data goes on the wire, that's where we want the protection. So we would focus on efficiency, and this is how we made our crypto implementations in the past. So for instance, this is a chip for the AES Randall algorithm, which we made a while ago. And you have even companies that add specific instructions for performance reasons for specific algorithms, like this AES instruction. Randall is the old name of AES. It's also designed from our research group in COSIC. And after it was accepted as the American encryption standard, so Randall became the AES instruction. Now, this model that we had, this old model which focused on performance, doesn't hold anymore. So the current model is actually where this distributed IoT, the current model is one where we assume that crypto sits in all these little devices, but crypto can be attacked. Crypto can be attacked. There is side channel attacks, power attacks, EM attacks, timing attacks. I even put in this category micro-architectural attacks, AI attacks, many things we saw today. And so the assumption now is that we still want crypto to protect our connections and security protocols, but we also need secure implementation. So it's not just about performance, but it's also about resistance to attack. Those two should be in place. So we need secure implementations, not just secure algorithms. And these have a price. The price is that you have, for instance, increased area or increased energy consumption. So in this case, we made some chip, and the protected version is about almost 3 times bigger than the unprotected version, but this one was resistant to side channel attack. So what is then hardware security? Depending on who you talk to, and the operating system designer will say, I will have to trust. For me, the root of trust is the architecture or the microarchitecture of a processor. If I'm talking to a network system guy, this person will say, for me, the root of trust, I have to trust the router box. That's a big box, right, to trust. The cryptography guy will have to trust maybe the VHDL Verilog code that's gonna run on the FPGA. An IoT device resistance means I need to resist side channel attacks. I need to resist attacks, fault attacks, manipulations. I might have to trust the standard cell design. I might have to trust the technology. Maybe some Trojan circuits are sitting in there, right? So we want, but how do you take that all into account? How do you make like all these requirements? So they can only do that by having what's called a design methodology, figuring out how do I translate all these security requirements for my hardware design. So we split it up in different levels, right? So we start at the application layer, and we say, okay, what's the application we have? What does it need? It might need some security protocols. The security protocols for implementation we need or relies on secure algorithms, because protocol designer assumes that the hash function he uses or the yes function he uses is correct. These algorithm designers rely on the fact that they have a correct architecture, that it's correctly implemented. Though those rely on the fact maybe there's no microarchitecture. Spectral meltdown is not considered here. All the way down to circuit resistance. I have to resist side channel attacks, and I might have to resist, like I need reliability, maybe I need puffs or whatever, right? So why do we have all these abstraction layers? We have these abstraction layers to get order in the house, to identify what is the weakest link, and actually at the end to be secure, right? And so that also relates to the root of trust at each design abstraction layer. The application says, I need a TPM. But the designer of the TPM will say, I need security protocols. The security protocols say, I need hardware, and so on. So we go all the way to the bottom. And so in these design abstraction layers, a root of trust is a component at a lower abstraction layer. And you want to minimize it. And the root of trust is upon which the system relies for its security. So the architecture guys rely on the microarchitecture guys. These rely on the circuit guys. And so you try to minimize. These rely on technology. There should be no row hammer attacks, right? So this was some of all these architectures was part of this whole analysis, and parts of solutions were part of the first ERC grant. So I have few slides left on what is next. So what are the topics I think hardware security is not finished. Of course, everybody works on AI now, so we have to take into account that there is AI, although Ahmed doesn't believe in it. So what are we working on next is actually, I think we have the new attacker on the block, and that's the quantum computer, right? Quantum computer is the new attacker in the game. And because I consider AI attacks as being part of the game already. They fit in my current trust model, whether it's just a more intelligent side channel attack, right? And also I would say this trend from cloud to IT to sensor nodes is not stopping. It's really electronics are dispersed into their environment. I heard someone talking about how your paint is going to be intelligent, right? You have paint, you act electronics, and you smear it out over the wall, and the paint is going to be intelligent, figure out when there are people, so when it has to be heat up, for instance, or make it comfortable for you. So, but how do you add security to that thing, right? So the research topics that we are looking at now is crypto that can maybe fit in post-quantum crypto. That fits in sensors but it's post-quantum secure. The other extreme is looking at operations for secure operations in the cloud, the so-called fully homomorphic encryption. Of course, we work also Prof, TRNG, new diversity in compute platforms is also important for it. So this is, maybe it hasn't been talked about because besides AI, another buzzword these days is quantum computing. So there is a lots of EU funding in quantum computing. But if we go for quantum computers, we also need what so-called post-quantum secure crypto. And why is that? That's because the mathematical foundations of existing public key algorithms will disappear. And so people are looking for new post-quantum secure algorithms, and most of them, or the ones which are most advanced, are lattice-based. This is just a representation of a lattice-based scheme, upon which the lattice mathematics upon which you can build public key design. So we spend these days a lot of time and invest a lot in the so-called NIST post-quantum standardization effort. NIST, so in the past it had a standardization effort on SHA algorithms, on the AS algorithms. At this moment, there is a standardization effort on post-quantum crypto. We're currently in the third and last round. There are 3 lattice-based finalists, of which Saber is one, and Saber is the submission of KU Leuven, of our research group. And what's interesting to see is that NIST realizes that you don't only need secure crypto, secure mathematics, but you also need secure implementations. So in the last document of NIST, which is a focus of around 3, it really says NIST encourages additional research regarding side channel analysis, and this is the case for each of these algorithms. So this is one topic which I think is important, which we are working on. Another topic which we're working on is actually, and that's interesting for the cloud people, and that's interesting for the people that want to do AI on the cloud. So I'm linking my research here to AI and the cloud. And basically what homomorphic encryption promises is that you encrypt your data, you store your data encrypted in the cloud. For instance, this is the case for medical data. And then, of course, it needs to be stored encrypted in the cloud. But then you sometimes want to do some machine learning AI type of operations. The problem is on encrypted data, you cannot do regular AI operations. You first have to decrypt it. But we don't want to decrypt. We actually want to do AI on the encrypted data. And that's the promise of what's called homomorphic encryption. And there are, at this moment, many schemes are being presented. The problem is that they're highly, computational demanding. So we really need cloud infrastructure to calculate those. And so this is the concept. So you encrypt locally, you store in the cloud, you do some operations, the encrypted data comes back locally, and there it can be decrypted. The thing is that this is very expensive. It's blow up in the amount of the size of the data. So the keys and the ciphertext are extremely large. It's also blow up in the amount of operations you have to do. So some experiments, and this is like an experiment we did on the FV van Verkouter scheme. which is actually quite small. It can only handle a neural network up to 4 levels deep, while we just hear the presentation where people go for 1,000 layers and things like that. So this guy can handle 4 layers. Still, it fills up my complete FPGA. And you can see how big it becomes because, say, small amount of data, I'm not even sure it was 6 bits, but a few bits of data, plain text, results in large ciphertext. In this case, it was 180 kilobytes of ciphertext. And then we're doing experiments on this, on FPGA. So this is an experiment we did of a dedicated specialized accelerator for homomorphic encryption on the Amazon cloud, where you see dedicated units, things like that, huge amount of parallelism. And I think this is research which can still go on for a couple of years. We see some benefits by using FPGA acceleration, for instance, versus GPU. You can also run GPU in the cloud. With FPGA, we could, this FPGA acceleration, we can do now more than 600 homomorphic multiplications per second. It's a speed up compared to highly optimized Intel or CPU implementations. And compared to GPU on the cloud, our estimate, it's about 3 times more cost efficient. And especially what's very important on the cloud is going to be more power efficient. And if you use the Amazon cost calculator, you can see that it also becomes cheaper, right? Because I think because of the power consumption. But now I notice that you cannot see my pointer. I have been using this pointer the whole time and you cannot see it. I'm so sorry about that. But so to the right bottom, you can see that the monthly cost for one FPGA, which can do much more multiplication, 2,000 multiplications, homomorphic multiplications would cost $1,200, while one GPU, which can only handle 388 multiplication, is more than $2,000. And I think the reason of this price difference is probably also because of power costs, energy costs that Amazon have to pay. I'm sorry, nobody tells me that I can't see the pointer, right? So I'm not sure you're paying attention. Okay. So this brings me also to my last slide. So I think for hardware security, and I still enjoy working on the topic, we have really combined challenges. We want it to be post-quantum secure. We want it ultra low power. We want it side channel attack, AI attack resistant, and we want it to fit all in IoT devices, right? Fit IoT devices going all the way to the cloud. So I think for the last 20 years, we did design for low power. So I think for the next 20 years, we will do design for security. And since there might be PhD students here, I'm looking for PhD students to work on this topic of homomorphic encryption, which is actually the second ERC grant. Thank you. This one is called Belfort.
Thank you very much. Any questions? If there are questions online, if there are some, please let us know.
Yes. I was wondering, you talked about your first or the first DES chip that you made. I was wondering what the status was of the design tools at that moment. Like, I can imagine that you didn't have like the same support from the tools as you would have now. So were there more things that you had to do manually back then?
Yes, we had to do lots of things manually. And if you go back to the picture, can this thing go back? Yeah. No.
Can you,
Just. Let's go back. You can see it at the layout.
Yeah, I thought so, because it's more like irregular than what you
so this was the start of logic synthesis tools. So where is my picture here? So yeah, I don't have a pointer. I was going to use the mouse, but I don't see it. So in the middle, you see very regular structures. You can actually recognize visually that's routing. At the bottom, we start at the bottom. These are S boxes. This has 8 S boxes, which were generated. They had a tool which was called a PLA generator. Some kind of regular synthesis tool. And then the rest is handcrafted, a bit like you make an SRAM. You make one cell and you try to see, can I copy paste it in the X and the Y directions? It's handcrafted. And then at the top, basically, this was the start of logic synthesis tools. Synopsys we didn't have, but there was a group in Leuven and Leuven. They had their own logic synthesis tool built, like an experimental tool. And so that's how we did that one. But lots of it is handcrafted. I don't think it's side channel secure, although it has very regular structure.
Thanks.
Yes, and then talking about startups. So there was a startup in Leuven. Actually, this was also the start of IMEC, I think, at that time, or IMEC existed a couple of years, but IMEC has to promise that they do startups, right? And so they were this was put in the startup. They were licensed because they also had an RSA accelerator, this company. And but the company was a bit mismanaged, I would say. I visited them a couple of times. They spend a lot of money on nice offices. I said, wow, they have beautiful desks here, and I have to, this old desk, PhD desk. And then, so IMEC sold the IP to this company. The company went belly up after a couple of years. And then what was actually misnegotiated by IMEC is that the IP did not come back to IMEC, so the IP was lost. And actually the founder of that company, once it went belly up, got personally bought on the IP, assuming that maybe he can use it again or reuse it or something like that. It was a little bit of a weird story. So I didn't make money.
But maybe now you are going to make money.
Yes, yes.
Redirect the ERC to your own bank account.
Yeah.
Okay, any other question? There's a question there.
Hi, thank you first for the presentation. You mentioned in one of your slides that you are interested in one of the key encapsulation mechanisms in post-quantum cryptography, which is SABRE. So I would like to ask you, did you consider one of the latest attacks, which is a machine learning side channel attack against the masked version of SABRE? And if you are considering countermeasures against this attack in SABRE, can you give me a brief?
So yeah, masking is a technique to add side channel countermeasures, and indeed some of older masking schemes can be broken, but the schemes that we are currently working on, or some of them have been put online, are resistant to these attacks. So I don't know which masking scheme specifically you are referring to.
Actually, I can show you the paper later.
Yes.
I don't really recall the details of the masked scheme, but I was interested how efficient would be machine learning combined with side channel attack to attack the masked versions of any post-quantum scheme in general, I mean.
I think in that sense, and I think Ahmed will agree, a perfect security does not exist. So we measure security, side channel resistance by, the first thing we do is TVLA tests, leakage tests. So we try to make them constant time. We also aim at making them resistant to first order, second order, and so on side channel attacks. And those are again also measured by TVLA tests and practical tests in the lab. So if you can point me. I also don't know if the mask implementation you're talking about was made by my students or was made by someone else?
No, actually, I think the paper was by the University of Sweden, KTH or.
Sorry. But masking was from COSIP, but that's very recent. That's just paper now.
Yeah, I'll check. We'll check it.
But it's always like you said,
Yeah.
Countermeasure.
Yeah, countermeasures. So we are working on new generations of attacks, right? Attacks and countermeasures. Okay, I'll check it.
Thank you.
More questions?
Okay, if there are no more questions, then I think, jump to the next talk. Yeah, you agree? Ingrid, before you go, also a handmade with love and with many greetings from our, no, I'm just joking. A student didn't do that indeed.
Wow.
But I hope you like it. It's a small
Thank you.
recognition of your fantastic talk, but also the fact that you came here.
Okay.
Thank you.
I
very
enjoyed.
much.
Thank you.